All right. Hello, everyone, and thank you for joining us today for this week's session of the Parks College weekly webinar series. My name is Amy, and I'm the outreach coordinator here at SLU's Parks College. I'll be joined today virtually by Dr. LeBeau, who will be sharing information with us about the Aerospace Engineering program and Computational Fluid Dynamics. We are very excited to have you joining us from wherever you are. Thank you for taking the time to virtually visit and learn more about the engineering programs at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management, and physics. We hope that you'll hear or see something today that piques your interest. Throughout the webinar, we do encourage you to submit any questions you may have to the Q&A feature at the bottom of your screen if you are viewing through Zoom, or in the comments section if you're viewing through Facebook Live. And we'll do our best to answer as many of those questions during the last few minutes of our session. Throughout this webinar, you don't need to worry about turning off your microphone or camera. You can hear and see our presenters throughout the webinar, but we cannot hear or see you. This session will be recorded and posted to our YouTube page in the next few days, and you'll receive an email with that link when it becomes available. If you would like to view any of our previous webinars, you'll also find those recordings in a Fall 2020 playlist and a Spring 2021 playlist on our YouTube page. So now, with that introduction finished, I am very happy to introduce Computational Fluid Dynamics and our Aerospace Engineering program. So Dr. LeBeau, I will let you take it from here.
All right, thank you, Amy. So what I want to do is first take you back about 30 years. And those of you who may remember this or not, but Voyager 2, which was the last and only mission to the outer planets, not counting Pluto, obviously, but in terms of Uranus and Neptune. And this is a video of the approach of Voyager 2 to Neptune. And so I want you to watch this video because it's going to kind of introduce why computational fluid dynamics is an important aspect of fluid dynamics study. So as you can see, Voyager 2 in this video is approaching Neptune. This is a series of still images, obviously, that have been spliced together in a video. And you can start seeing. Yeah. Oh.
Sorry, we're not seeing anything.
Okay. Stop that. Apparently my attempt to do screens grab did not work. Let me try one more time. Sorry about that. Sometimes the screen share on my computer seems to not want to share.
All good. I'm seeing stuff now.
Okay, yes. Good. Sorry about that. All right, so we'll go back to it. Anyways, so what we're looking at here is the approach of Voyager 2 to Neptune. And what we can see is that as we get closer to Neptune, which again is the 8th planet in our solar system, and with the downgrading of Pluto, the last planet in our solar system relative to distance to the sun, you start seeing this very large feature come into view. And this feature is known as the Great Dark Spot. And what was fascinating about it, or one of the many fascinating things about it, is that it actually changed shape, which is very unusual. If you're familiar with the Great Red Spot, it doesn't change shape. It just kind of stays roughly the same size and has been there for hundreds of years. This was quite a different phenomena. It's something that we had never seen before on Earth in natural situations or on other planets. But the problem is that once Voyager 2 flew by, that was it. We couldn't study it anymore. By the time the Hubble Space Telescope got into operation a few years later, this was gone. And so we don't have the capabilities to actually look at this in any great detail beyond just what we had from these few snapshots from Voyager 2. So, well, what can we do at that point? Well, one thing we can do, of course, is conducting experiments. And what I have set up over here is, in fact, the kind of experiment that you can do. This is known as a rotating water table. So what's happening here is the fluid has been rotating now for about a half hour or so. And so it's achieved what's called solid body rotation, meaning all the fluid is rotating the same way. And so what I can do with that is I can go ahead and insert, I'm going to stand up here for a moment and cut it off. What I can do is I can insert a little bit of dye so we can actually see the water, because obviously water is hard to see inherently. So I put a little drop of dye in here. Then what I do is I kind of swirl around a little bit to get it moving. And what's going to happen is we're going to form a vortex. And if you want to see that vortex, you can see it up on the screen over here. And I'm going to bring my computer up a little bit closer so it's a little bit easier to see. We're looking at it this way because if you try to look at it in the water itself, we'd have to keep spinning our head around. The camera, as you can see over here, is fixed to rotate with the water. So we're seeing it in the rotating frame of reference. And you can quite clearly see we have three nice large vortices formed here. Now the great dark spot was only one, and with a little bit more control, you can create that type of environment. And you can see we have three very nice vortices formed here. The problem is, this is about the best that we can do in experimental modeling. We don't control the weather. We cannot recreate something that's thousands of miles across, as the great dark spot was. And so doing an experiment like this, maybe there are some that are quite a bit larger, rotating tables like this are quite a bit larger, but we can't really easily recreate the conditions that created this phenomenon. So one way we can account for that, or one thing that we can do beyond that, is resort to simulating this on a computer. I'm sure you all are familiar with meteorological models, weather models that are used to predict the weather. So we can do something like that for Neptune as well. But what underlies those weather models is a process known as computational fluid dynamics. And so what we were able to do is I'm going to go back to sharing the screen here. What we were able to do is we were able to look at this phenomenon and just a little bit more information about it. Again, it was about 38 degrees by 14 degrees across. So 38 degrees horizontally, 14 degrees vertically in terms of longitude and latitude. And it had this 8-day oscillation that you saw the video of, where its shape changed, going from kind of a roughly elliptical shape. It got stretched out, eventually formed these little tails, and then gradually the tails disappeared and returned back to kind of an elliptical shape. And did this 3 or 4 times in our viewing period. And it also drifted from south to north. It was in the southern hemisphere, and it drifted northward toward the equator. And it did this about 1.2 degrees per month. And we saw it visually, or signs of it, with the Voyager observation for about 8 months. Initially, you just see the bright cloud, and then gradually the dark spot came into view. So there's a lot of interesting phenomena going on here, but like I said, we couldn't really mimic that in the lab. We didn't have the ability to do experiments, but we were able to mimic it on computer doing simulations. So this is a video of a simulation of the great dark spot. And as you see this line develop, you watch the dashed line here indicating the outer limits of that dark spot. You can see it forming tails. You can see it oscillating in shape. And it captured a lot of the characteristics that we see in the images from the great dark spot. You can see some of the tails kicking off there right now. And so by doing that, by using a computer and doing a simulation, we were able to represent what was happening in that flow field on Neptune. So part of the reason for introducing this is it's an example of why we do what's called computational fluid dynamics. Computational fluid dynamics is essentially taking the information, or taking the information about fluid dynamics and taking the physical characteristics of a particular situation and replicating them on a computer using a computational model. And so in the case of the great dark spot, the computational model that we used was called EPIC, shown here, kind of the head of it. And what you have to do computational modeling is what we do is we break the problem down into really tiny parts. So we don't simulate the whole thing in a big blob. We break it down into little pieces. And you can see this is what's called, in this case, it's called a grid. And so we created a series of points which define the properties of the flow at those points. So we can't define everything. It's not a continuous solution. It's what's called a discrete solution. It's a solution where we're actually solving the problem at a series of points representing the entire flow field. And what we solve are essentially conservation laws. Now, these are not probably the conservation laws you're used to looking at the form, but they're the same things you learn in many high school classes: conservation of energy, momentum, and mass, written a little bit differently because it's fluid dynamics. But that's what we solve. That's really what computational fluid dynamics is. It's breaking down the problem into small parts, applying your conservation laws to those small parts, and then calculating it over and over and over and over again until all the conservation laws are satisfied. And that's the underlying basis of computational fluid dynamics. And so there's many reasons why there's advantages to solving fluid dynamic problems on computer versus doing experiments, and certainly versus solving it by hand. In fact, for the record, the first effort to do computational fluid dynamics was weather related, and it was by hand. Scientist named Richardson back in the 1920s decided to try to recreate the weather that was seen from a series of weather reports during the 1910s. And it took him about 6 weeks to do the calculations to represent 6 hours of weather. And turned out he wasn't terribly accurate. But that still is the first attempt for somebody, and he had to try to calculate a fluid dynamic problems using this method of breaking it down into small parts and iterating many, many times to get the answer. And he actually envisioned having a huge sphere built where there'd be people at various latitude and longitude points. And doing that, he'd be able to have essentially a computer calculating the weather all around the world, except the calculations will be done by people and by hand. So it wasn't necessarily going to be very quick. For the record, the first actual credited CFD calculation typically is one that was done in the early 1950s. It was also weather prediction, and it was able to do, and it was done on a computer, and it was able to predict the weather about as fast as the weather was happening. It could do about 24 hours in about 24 hours of calculation time. So that's often credited with being the first true computational fluid dynamic application. So weather has played a big role in the development of computational fluid dynamics, be it on Earth or on Neptune. However, weather is not the only place, obviously, where computational fluid dynamics happens. It's also used extensively in a lot of other engineering fields, and in particular in aerospace engineering. So what I'd like to show you next is a more classic aerospace example. This is actually a simulation of, I'm gonna go ahead and stop sharing here. This is actually a simulation that that is currently running. And what it is that it is a simulation of a probe entering the atmosphere of Titan. Now, Titan, for those of you who don't know, is one of the moons of Saturn. There's currently a mission under development by NASA to actually send a small aircraft to Titan to fly around and investigate the atmosphere. And the reason why we're interested in Titan is that it has a nitrogen atmosphere very similar to ours. The pressure is about 50% higher, but it's in many ways the closest atmosphere to Earth's. It also contains rain. Now, it's not conventional rain, it's not water, it's methane and ethane and other hydrocarbons, but it still has a liquid surface in places, which is the only other body in the solar system which has continuous liquid surfaces, as far as we know. So we're interested in sending probes in there. Well, these probes are going to enter at very high speeds. And in this case, this is a simulation of how this probe entry into the atmosphere of Titan. So I'm going to go ahead and run it a little bit as a movie here. What we're seeing here on the screen is we're seeing get the mouse to go. There we go. What we're seeing on the screen is the horizontal velocity, the velocity in the direction of the entry. And you can see it, the full run reaches velocities of about 4,200 meters per second, which, if you prefer to think in miles per hour, is about 8,500, 8,700 miles per hour. So this is moving incredibly quickly. And so the time that passes during this movie is actually very small. We're going to go ahead and start from the beginning, and we're going to look at how this flow field evolves. Hopefully, there we go. So you can see initially there's no flow at all. And now the flow is slowly beginning to come in and encounter the probe, which is this little black region right here. And so you'll be able to see the probe a little bit more clearly as the flow approaches it. So this is a series of images that we've calculated using computational fluid dynamics. This is using a open source code called High2 Foam, which is a variation of the open source baseline OpenFoam. And it essentially does the same things that I talked about with EPIC. It breaks it up into lots of small volumes, the problem up into lots of small volumes, and then it solves the conservation laws. Now this one's a little more complicated because this is hypersonic speeds. So we have to worry about shocks, we have to worry about chemistry. There's other aspects that have to be brought in along with the basic fluid dynamics. But you can see the shock forming quite nicely in front of the probe here. And you can see some of the wake coming off the probe and how that's changing the velocity field as it comes off. And so this flow will continue to move downstream and the shock will continue to develop, and will develop a little bit longer here over the probe. Now the time elapsed here, right now we've only gone about 3/10 of a second, or sorry, 3/100ths of a second. Now, of course, if you're traveling at 9,000, 8,500 miles per hour, that's actually a lot of distance. But this is the kind of time frames that we sometimes have to do these calculations on, because it takes a long time to do all these calculations to represent this flow field. So even today, I was talking about how the weather prediction went 24 hours to predict 24 hours of weather. This one has taken months to be able to predict 0.05, 0.06 seconds of the flow field. All right. But this is another thing that we can do that's not easily accessible in a lab. It's very hard for us to recreate hypersonic conditions. The Mach number at the end of this is about a Mach of 16. So we're traveling about 16 times the speed of sound, plus to mimic the conditions in Titan's atmosphere. So in a lot of ways, we have to rely on computational fluid dynamics in order to solve this type of problem. All right. So I'm going to talk about a couple more CFD problems that we're working on here at SLU, in addition to the ones that I've just showed you. And these are more conventional aircraft problems. So I'm going to go ahead and share the screen again. So one of the problems we're working on is one, I used to be at the University of Kentucky and we did some work there on this, and it's carried over to here. And what this is looking at what's called an inflatable airfoil. And what we have is an airfoil that you blow up like a balloon or a beach ball. But to keep the shape, we have to put in these baffles. And these baffles serve to hold the shape. But what happens because of the baffles is you get extra inflation between the baffles. So your surface, instead of being smooth, ends up looking like a series of small bumps. And so this creates some interesting effects aerodynamically. And so this is another way that we can use CFD. This is something we can put in a wind tunnel. Those of you who are interested in the wind tunnel work, I know we had a previous version of this seminar last semester talking about our wind tunnels, and you certainly should go ahead and check that out. But what we did is we could go in the wind tunnel and actually take data, which is basically looking at fog. And then we can use that fog and turn that into a velocity field. So these are a lot of little tiny velocity vectors. And you can see this region down here where the fog fades away over the surface. That's called separation. And so you get a lot of swirling in here. We can see that in the velocity vectors. But then what we can do is take a CFD simulation of that same phenomenon. And we can check it. So this is a process known as validation. It's very important for CFD to have some idea that what you're doing is actually right. So this is actually a comparison of what's called the reverse flow probability, which is the likelihood that the flow is going backwards instead of forwards because of this separation. And so we're comparing it under different conditions. This is what's called the Reynolds number, which is a representation in this case of the velocity of the flow. And then the angle of attack, how much the wing is tilted. And you can see we got a nice smaller area here, and it grew up roughly in the same shape as we went to a higher angle of attack. And so we were checking how good our CFD results were. But once we had those CFD results, we could start doing comparisons and get more detail out about the flows. These are a couple of CFD videos showing the difference between a smooth airfoil without any bumps and the flow field when we have lots of bumps, like the inflatable airfoil. And you can fundamentally see the difference in how the flow fields behave. And as a result, we were able to figure out that at relatively lower speeds, again, represented by this Reynolds number, the inflatable airfoil, by creating more mixing, helped break up the separation that formed on the smooth airfoil. And it actually might have better aerodynamic characteristics. Once we get to faster speeds above a Reynolds numbers around 100,000, that effect kind of went away. So that gave us a lot of insight into the physical phenomena. So another use of CFD is the ability to replicate things that we can do in the wind tunnel, but because we only can measure so much in the wind tunnel, in this case, we could measure the velocity field and that was about it. I can get all sorts of data out of this CFD run now, like the pressures, the densities, the vorticity, the turbulence, all sorts of things can come out of the CFD run that I couldn't easily get out of the experiment. So a active example of how we can use this is going on right now. We're doing a process, we're doing investigation. This is along with Professor Gururajan, who I think is, you may hear from next week. And what we're doing with this is we're actually combining CFD, wind tunnel, and flight testing. And what we're doing this on is damaged wing sections. So I have right over here an example of that. So this is a damaged wing section. And it was damaged actually by firing ice pellets at it out of an ice pellet gun. And so what we're trying to do is see, using a combination of flight testing, wind tunnel testing, and CFD, how the behavior of the wing is affected by this type of damage. And the idea is ultimately to be able to develop controllers that can compensate for the damage that is shown on these wings. So if a wing is damaged somewhere, the plane will actually be able to automatically compensate for that damage and still continue flying. So this is kind of the last example I wanted to show you about CFD. There's a wide variety of other applications that go along with computational fluid dynamics. And there's some that I aren't able to show you because of time. So again, these are some of the areas, just generally computational fluid dynamics, but UAV aerodynamics and flow control, planetary atmospheres, as we've seen, and also a device known as a plasma actuator, which unfortunately there wasn't time to talk about today. But I appreciate everyone coming out and learning a little about computational fluid dynamics and CFD. And I hope that this has inspired you to investigate, if not CFD, other aspects of fluid dynamics. Thanks.
Thanks, Dr. LeBeau. This was very interesting. I'm very intrigued by all the different applications of it, and also slightly overwhelmed as someone who has nothing of an engineering background. So our students in our aerospace program, they take a CFD course. Is that correct?
They do a little bit of CFD in their regular courses, and they do a little bit in the lab. The full scale CFD course is an elective that they can choose to take in the latter stages of the program.
Okay, so we do have students who kind of go on to maybe specialize in.
Oh yes, we certainly do. There are a number of we have a number of graduates who have worked in computational fluid dynamics at this point, and a lot of students find it a helpful skill. Even if you're not working in computational fluid dynamics, many students work with, or graduates work with people doing computational fluid dynamics. So it's useful to have some knowledge there as well.
Gotcha. I am wondering, I think that the interplanetary atmospheric science is very fascinating. Do we have a lot of graduates that like go on to work for NASA and apply this knowledge there?
We haven't had a whole lot of people come out in that direction. Because it's a combination of aerospace and meteorology. And so, and there's also planetary scientists, people who are planetary scientists. So there's a lot of different intersections of fields in this area. We've had a few grad students go out and work with this. But if you want to do that, it tends to be more at the graduate level than ultimately you have to get to the graduate level to be able to really work in that particular field because of the complexity and the multi-physics involved.
I imagine. Okay, so very specialized work. And I was wondering if you could expand a bit upon your project with Dr. Gururajan. Like, what's the time frame of that kind of project from beginning to end, and then how much of this project spent running simulations?
So this project has been going on, I'd say, a year and a half right now. We're at the stage now where we are doing all three pieces of it. The CFD, that we've done the wind tunnel, and we're doing flight testing. There's still a lot more CFD that could be done. The CFD in some ways is the slowest aspect of the project because it takes weeks to do a good simulation. And so We can only do so many of those simulations at a time. And there's a lot of different configurations out there. But again, the point of the simulations in this case is to help capture or measure things that we can't in the flight testing and the wind tunnel testing. So right now they're actually working, well, I don't want to do too much, but they're working on the analysis of the data from flight testing and trying to see how that can create some initial controller software in the system.
Gotcha. Gotcha. All right. Well, this was all very interesting. I'm going to do one last check for any questions that might have come in while we were talking. And I'm not seeing any. So thank you so much, Dr. LeBeau, for taking us around and showing us this aspect of aerospace engineering and for sharing your time with us today. I also want to thank our viewers for joining us and hope that you enjoyed this visit to SLU's Aerospace Engineering program. If you would like to learn more about our engineering programs, please visit slu.edu/parks. Please join us once more in this space next week. It'll be our final webinar of the spring semester when we'll be showcasing our drone lab and another side of our aerospace engineering program. That will be on Friday, April 23rd at 2 p.m. All right, so this concludes our webinar today. Thank you again for joining us, and I hope everyone has a great rest of your weeks.
Thank you.
Bye.